Good morning, everybody. Hopefully everyone had an enjoyable long weekend. Start with some green check marks, please, and then we'll get started. Nice to see almost everyone in class today. That doesn't happen very often. I shouldn't say almost everyone. We're missing a bunch of people, but there's a lot of people here today. So last day we were looking at Half-Life, and we had to leave a bit early, so I left you guys with some questions to go through, and I wanted to go through a few of them with you because they're hard, they're difficult until you see them done a few times. So I want to jump into some Half-Life questions out of the learning guide. Then we'll do the nuclear reaction stuff, and it's just more of the same. It's kind of like the alpha, beta, gamma stuff. So I want to do those two things, and then the lab with the handout sheet that I asked you guys to look at with the decay simulator online that you guys were supposed to do last day. I'll have just a peek at that before we're done today as well. Perfect, Costin, thank you. If there's anything else, I'm sure there's a bunch, so I'll just do a bunch of questions. Got my pen working this morning. Always a bonus when I can write. Page 6, number 12. All right. So when we talk about Half-Life, you can look at these kind of graphing type questions and trying to identify where half-life is on a graph at 50% or half of your sample. We can also do with no graph, with just doing some basic math. So let's see if I can get the page 3, that's back a ways here, Costin. 4, page 313. So page 313, Costin, just out of there's a table in the notes. Let's see if I can find it. I went through this a few times. Should be under here. So the difference between alpha, beta, gamma, and their charges, and what they can be stopped by. Let's see if this is it. Nope. There it is right there. So that was a couple classes ago now. Just kind of summarizing these two charts behind me here, the alpha, beta, gamma stuff. So that would be a good place to look for the information for that question, Costin. The other stuff that we wanted to go through was some of the more recent Half-Life questions, and I think that's what Eric has a question about here. All right, so this was still looking at alpha, beta, gamma, then we get into the half-life. Just scrolling down to your question here, Eric. Maybe I'll start with 5 and then I'll get to number 12 in a second here, Eric. So just kind of to refresh our memories, just to take a step back. There's lots of different ways to do these questions. I'll actually show you guys a formula which you can use, and the course doesn't really do a good job of explaining the formula, and rarely will you ever need the formula. Everything will kind of work out fairly straightforwardly, but there's a few questions where you will need, you might need, or it makes it easier to use this formula. The problem is that the formula is not on your formula sheet, so you just have to kind of memorize it. I want to do these questions, and I always draw a chart or a table for them just to kind of organize everything. And I find it works really well to kind of organize your thoughts and just try to get everything straightened out. So when we're talking about half-life questions, I usually have a chart with half-lives. I have something like percent or mass. That's all we need for this question. You could have time in here as well, and mass. So you could have a chart like that. we don't need all of that right now. All we need is number of half-lives and percent, because it says how much percent of your parent isotope will be left after 4 half-lives. So I'm going to lose some of the stuff on the side here, and we'll just go through like this. So I'm going to always start at 0. And when I start at 0, I have 100% of what I initially started with. So 100% 0. Generally speaking, all of these, it's best to start with 0. Start at time 0. That's the very start of your experiment. And then 1 half-life passes, and you should have 50% of what you started with. Then another half-life passes, and you should have another half. So don't take 50% away. It's not minus 50% life, it's half-life. So 2 half-lives. I'll continue the chart over here. Half-life and percent. I have 3 half-lives, it's 12.5, and then I have 4 half-lives, and it's 6.25. So what percent of your parent will be left after 4 half-lives? 6.25%. You could just, on your calculator, go divide by 2, divide by 2, divide by 2, do that 4 times, and you're going to end up at that 6.25. So there's questions like that. Question number 6 is tricky because it's not going to be an exact number. If you are at 20%, that's not going to be, it's asking for 1 decimal place. So you're just going to have to do your best to estimate it, and that'll be good enough. You don't have to really worry about getting exactly on 20%. So if you were to think about this exact same question as the previous question, they're quite closely related, but it's asking how many half-lives would I be at if I made it to 20% of my initial sample. So if I look at the number of half-lives at 20%, I'm going to be somewhere between 2 half-lives and 25, and 3 half-lives is 12.5. So somewhere between 2 and 3 half-lives, and it's probably a little bit closer to 2, so you can just estimate it, maybe like 2.3 half-lives or something like that would be fine based on the previous question. So that's good. Get us started. We looked at that, page 6, number 12. So let's maybe look at 11 first, Eric, and then I'll get to 12. Again, draw a table. Just kind of helps organize instead of randomly dividing numbers on your calculator until you think you get to where you're supposed to be. You'll notice in this chart I have number of half-lives, I have time, and I have the amount. So each question is going to either have a percentage or an amount in grams. This particular question tells me I have 1,000 grams to start with. So I don't really need a percent column. I mean, I could do a percent, but the question doesn't give me a percent, nor is it asking for a percent. So we probably wouldn't include that. But half-life's time and amount, and the amount is just a mass in grams. That would be a good place to start. So the fact that it tells you the isotope isn't extremely important. The half-life is 15 hours. We're going to need that. Our initial mass is 1,000 grams. We're going to need that. And it's asking for the sodium that would be left after 3 days and 12 hours. So this isn't just a question where you can just jump into things and start dividing and see where you end up. The problem is that it tells you that our half-life is 15 hours, but then it's asking how much is going to be left after 3 days and 12 hours. So we end up with this problem with units. I have a half-life in hours, and then I have the amount of time that's passed in days and hours, which is kind of confusing. So if I had 1 day, that's going to be 24 hours, 2 days, that's going to be 48 hours, 3 days, another 24, it's going to give us 60, 72 hours, and then I have another 12 hours. So that's 84 4 hours in total. So that is what kind of the time frame I'm dealing with here. So what I'm going to do is I'm going to plug the information into the chart, and then I'm going to see what happens, or see when I get close to this magic 84-hour mark. So I'm always going to start at 0 half-life, 0 time, and I'm starting with 1,000 grams. That's what I'm beginning with. Then I'm going to go through 1 half-life, and it tells me each half-life takes 15 hours to complete. So now I'm down to 500 grams. I'm going to go 2 half-lives at 30 hours, 250 grams. 3 half-lives is 45 hours, and 250, 125 grams. 4 half-lives, 60 hours, 62.5 grams. Did I get that right? 12 and a half, 62 and a half. Things get a little bit hairier after this. Let's continue on. Kind of ran out of room on my chart here. I'm going to have another 5 half-lives is 75 hours. So I'm getting close to the 84. I'm going to use my calculator now. So 62.5 divided by 2. Probably could have done that in my head. 31.25. And then after 6 half-lives, I'm at 90 hours, and 31.25 divided by 2 again. It's going to be 15.625 grams. So you notice if I use this table, again I'm going to run into this problem where my answer is going to be at 84 hours. That's what the question's asking me. After 84 hours, how much will I have left? And that 84 is somewhere between these two. So 2 ways to think about it. You can just estimate it the best you can between those points, or you can use the formula. And I'll show you how to use that formula here in a second. So it's a bit tricky because you're somewhere between 75 and 90. You're at 84, so you're a little bit closer to 90, and you're starting at 31 and you're going down to 15. So you're probably a little bit closer to the 15 end of the things. Now I have the answer written down already, so I'm going to just estimate this at about. It's going to be about 20 grams. And that's about as close as I'm going to get using the table to estimate somewhere between these two. It's going to be 84 hours and about 20 grams. Okay, so assuming that you remember a formula, here is your formula. And again, I don't know why the learning guide does this. In the provincial exam and the questions you deal with on your final exam, they're all going to work out nice and round, and you don't have to worry about estimating. But this y is a to the 1, or sorry, a 1/2 to the power of x. So let's maybe write this formula down above, and I'll explain what everything is. You can just put it on your page. If you can remember it, it's just kind of a quick way of going through things. Y is a times 1/2 the power of x. So the a is your initial amount, and then the x is the number of half-lives you've lived through. So in this particular question, we could do it using, yeah, Madison, it did. So we don't have to worry about it. So how many half-lives do we have? Well, we have 84 hours is our total time. And then we're going to divide it by 15 hours to give us 5.6 half-lives. So one half-life is 15 hours. If I take the total amount of time divided by the amount of time it takes for one half-life, I have 5.6 half-lives occurring in this particular example. So that's where this 5.6 is coming from here. So I have y is 1,000. My initial amount was 1,000 grams. Plug that into my equation. Is 1,000 times 1/2 to the 5.6. And I need to just remember how to do this on my calculator. So I have to remember BEDMAS, brackets, exponents, division, multiplication, addition, subtraction. So I need to do my exponent first. And in this particular example, it's 1/2 to the power of 5.6. See if I can get this fired up. So I'm going to go 0.5. And then on my calculator, I have this little hat button. Yours is going to be a little bit different probably. So I get 0.5 to the power of 5.6. You might have a button that looks like x to the y instead of the hat. Sorry, Mr. Ross, I'll go back to calculator. You might have a little button that looks like x to the y. You might have the hat. Just depends on your calculator. Anyways, I'm going to hit enter, and I get this number, and then I'm going to multiply that by my initial amount, which is 1,000 grams. So I get 20.6. So I estimated it to be around 20. When I use the formula, it's 20.6. Again, all I want you guys to know how to do is use the table. If you can use the table, you'll be fine. If you want to remember the formula and remember how to use it and do all that, that's good too. But the important thing is just being able to draw the table, half-life, time, amount, and that's going to get you through all of these questions. The formula is going to be a more accurate way of doing it, a little bit easier possibly, sometimes more difficult depending on what you're looking for. But I just don't like the idea of just blankly memorizing things. So I'm not going to encourage the formula. Finally, Eric, we'll get to your number 12 question here. Thanks for your patience. This stuff out of the way. All right, the half-life of the isotope, maybe that's supposed to say strontium, is 87 days. Initial sample contains 30 grams of sulfur. Oh, it is radioactive sulfur. Sorry, probably shouldn't have assumed. Never heard of radioactive sulfur before. What mass of the sulfur? 35 will be left after 1 year. You'll need to calculate the number of half-lives that have passed to one decimal place and then use the graph on page 2. All right, so 1 year is 365 days, and we want to figure out how many half-lives have occurred. So just 365 divided by 87, because each period of 87 days is going to be one half-life. So if I go back to my calculator, I go 365 divided by 87. It's going to give me 4.195. We'll just go 4.2 half-lives. All right, so we know 4.2 half-lives have occurred. The initial sample contains 300 grams. So I could do a chart, or I could look at the graph as it asks me to do. So let's go up to the graph on page 2. 1, 2. I don't have a graph on page 2. Percent 4 billion years percent time. All right, so we can look at just this graph. Will work as well as anyone because they're all the same. The one thing that we need to kind of ignore down here is this is time in billions of years, which isn't going to help us very much because our half-life is much shorter than that. But what we can use from this graph is the dots. And the dots are half-lives. So that's 1 half-life, that's 2 half-lives, that's 3 half-lives, that's 4 half-lives. So in this example, it says we've undergone 4.2 half-lives. So it says how much is left after a year. Each half-life is 87 days. So we did a little math. We said, okay, how many times is 87 going to 365? We found that it was about 4 times. Okay, so we can figure out what percent is remaining. So after 1 half-life, I'm at 50%. After 2 half-lives, I'm at 25. 3 half-lives is 12.5, and then 4 half-lives is 6.25. But it's asking for 4.2. So I'm going to estimate at 4.2, which is going to be somewhere around here. If I went across, it's going to be about 6% remaining. So I start with 100. After 4-ish half-lives, I have 6-point-something% remaining. So if I go back to my question, I know that I have about 6% remaining. What did I start with? Well, I started with 300 grams. So what is 6% of 300 grams? Pushing buttons here. 0.06 times 300 grams. It's going to be 18, I think. 1.8 makes more sense. 300 times 0.06 is 18 grams. So if I start with 300 grams, after 365 days, I will have 18 grams remaining. Does that help you at all, Eric, or does that make you more confused? We can also use the formula. It says 16.3. We did the best we could with the information we have. Let's use the formula and see what happens. Again, don't need to memorize it, but if you want to use it, you can. How much is left? I'm not sure. I'm starting with 300 grams. I'm going to have 1/2 to the power of 4.2. So I'm going to plug it in my calculator, 0.5 to the power of 4.2, and then I'm going to multiply that by the initial 300, and I'm going to end up with 16.3 grams. Did you use the formula to get the 16.3, Eric, or did you do something else? Not sure? Okay. Was there anything else that you were running into problems with on these questions? Maybe we'll do 13, 14. I'll do one of these last two. Fossil is analyzed to determine the percent of original carbon-14 remaining is 25%. How old is it? 12 gram samples, carbons left in container 60 minutes. Mass carbon is now 1.5. What's the half-life? Why are they different answers leads? The reason they're different is because I used a chart to estimate this one. And then this one I calculated. The reason I estimated, because it says use the graph on page 2, but I don't know what graph it's talking about because page 2 doesn't have a graph on it. So I did my best with the information I had. I used one of these half-life decay curves to estimate it. Actually use this one. So I found there's about 6% left. It was a little bit less than 6%. So I just did what I could to estimate it. Now if I remember the formula, I can just plug it in and figure out exactly what the answer is, but I didn't have that luxury, assuming I forgot the formula. Let's look at number 14. I'll leave you guys to do 13. 12-gram sample of carbon is left in a container for 60 minutes. The mass of carbon is now 1.5 grams. What is the half-life of carbon? 11. So what we have to do is kind of maybe work backwards if you want to think about it that way. So my sample has let's not write sample, let's write mass, because I have a mass. And I'm going to have half-lives. I'm going to have time. So the question says that if the mass of carbon is now 1.5, what is the half-life? So at the very beginning, I start with 12 grams. That's 0 half-lives, and that's 0 time. 0 time has passed. Then I go through a bunch of half-lives, and I end up with 1.5 grams. I don't know how many half-lives it is, but it's at 60 minutes. So what I'm going to try to do is work backwards, because I know that each half-life is going to take the mass I have and divide it in half. I don't know if I put in the right number of lines there. 3, 6, I think I got lucky. I'm off by 1. So if I have 1.5 grams right now, if I go back in time, I know I'm going to double my mass if I could go back in time. So instead of having 1.5, if I work backwards, I have to have 3 grams here. And then if I work backwards again, I'm going to double it, and I'm going to get 6 grams. And if I work backwards again, I'm going to eventually make it to 12 grams. So I'm kind of working backwards because I know each step is going to take the mass and divide it in half. So if I go backwards, each step is going to actually double the mass. So I don't know anything other than that. But what I can figure out now is that I've gone through 1 half-life to get to 6. I've gone through 2 half-lives to get to 3. And I've undergone 3 half-lives. So now I know this is 3 half-lives to get to that 1.5 grams. The other thing I don't know is that the time, how long it takes to go from each step. But I can kind of figure that out because I know that the first step took some amount of time, and then the second step took some amount of time, and then the third step took some amount of time. And each time, the half-life is the same amount of time. So if the half-life was 20 minutes, which you can kind of deduce, and then I have another half-life is another 20 minutes, so I'm at 40 minutes. And then another half-life is another 20 minutes. Gives me to 60 minutes. The amount of time each step would take would be 20 minutes. So the half-life of carbon 12, carbon 11 is 20 minutes. So a little bit of logic. Hopefully we can work through these. Kind of have to work backwards and then work forwards. All right, did anybody have any additional questions from the half-life stuff? Did anybody have any questions from the sheet, that the kind of little activity thing where you were to download that little Word document and then follow the instructions and add some atoms and see if you can get them to decay and see what the graphs look like and what parent-daughter pairs you had? Questions on that stuff? Negative. All right, we shall continue then. So we've done 7.1, which was the different types of radiation, alpha, beta, gamma. And then we did 7.2, which was the half-life stuff we just looked at. Now we have 7.3, which we'll look at today. And the 7.3 stuff is really similar to the alpha, beta, gamma stuff, same sort of ideas. And we'll probably spend maybe like half a class next day finishing up radiation. Then we're done. Done radiation. 2 units to go. All right, so nuclear reactions. Here we go. We're going to talk about 2 different types of nuclear reactions, and there are 2 different types of nuclear reactions. We talk about fission and fusion, and the words kind of really sound the same, but they mean very different things. The beauty of these 2 types of reactions is that they release extremely large amounts of energy with very small, initial masses. So we can use the fact that really unstable big atoms like to break down. When they break down, they release a bunch of energy, and we can harness that energy as heat. And generally speaking, we'll use that heat to heat some water. And once we've created water, we've created steam, and then we can use steam to spin a turbine, and we can use the turbine to generate electricity, which is kind of what happens in our hydroelectric dams that we have in British Columbia, because we have lots of mountains and water and snow in the winter and things like that. We dam a river, the water flows through the dam, spins a turbine, the turbine creates electricity. So we're using gravity instead of the energy from nuclear particles. So we're lucky in BC to have lots of mountains and snow and rivers and things like that. In Ontario and Quebec, they are generally speaking a little bit flatter. They don't have as much hydroelectric power, plus they have larger populations than BC. So they use nuclear power to power things that they need, houses, industry. And Canada has their, I forgot New Brunswick. Canada has their own brand of nuclear reactor. It's called a CANDU reactor. And this is actually a picture of one in Ontario, I believe. And the reactor core, is probably in the domed building. I've lost my cursor. There it is, and it's gone again. Anyways, the reactor core is probably in the domed building, or it might be in this big rectangular building here as well. Nuclear reactors are always next to some sort of water source because they need the water to cool the reactor down, and they need water to spin the turbine once it gets turned into steam. So that's kind of what they look like. They don't look very special, but obviously they're very specialized. We sell our reactors, our reactor technology all over the world, and basically what another company would, or country I should say, would do is say, hey Canada, we really need one of your fancy CANDU reactors. And we'd say, okay, where do you want it? And they'd say, right here. And then we'd, as Canadians and the Canadian Nuclear Power sort of consortium would go over, they'd build the reactor for some foreign country, and they'd say, okay, let's learn how to use it. They'd show them what buttons to press and how it works and how to maintain it safely. And then the other country would have our Canadian reactor, and they could use it to generate power. So we're going to talk a little bit about nuclear fission first, and then we'll talk about fusion second. Different concepts. So basically, when you get really heavy atoms, really big ones, you have so many protons in the nucleus, all those positive charges, and you'll remember, hopefully, that like charges repel one another. So if you try to stick a bunch of positive things together, they're going to want to push away from one another. So once it gets big enough, anything past, once it gets big enough, there's so many protons there, it just wants to fall apart. It wants to break into two smaller pieces or more than two smaller pieces. And that's what fission is. Fission is a big nucleus that breaks down into two or more pieces. So when this fission, the breaking down is the fission, when it happens, you get a bunch of energy is released because it's now more stable, and you get these two things hanging out. And then you get a few more neutrons that kind of fly out because all those neutrons were in the nucleus. Once it breaks apart, it frees a few neutrons and they come speeding out of the nucleus. And that's essentially what happens. When we talk about a sample, let's say I had a few grams of uranium in my hand right now. Remember, in a small sample of a few grams, there's going to be billions of atoms there, massive amounts of atoms. So this is happening, thousands and thousands and thousands of times each second. So when you are in grade 8, I want to say, or 9, you talk about conservation of mass. And in chemical reactions, like unit 6, when we talked about chemical equations, whatever we started with was what we ended with. If we started with sodium, we ended with sodium. When we were balancing, I'd say that about 1,000 times. If we start with oxygen, we have to end with oxygen. Then we'd count, and then we'd balance back and forth. With nuclear reactions, it doesn't happen that way. One thing that does happen is that the actual atoms, the nucleus, it changes from one atom to a different one, which is kind of perhaps a bit confusing because we're so used to talking about just traditional chemical reactions where you start with something, you end with it. But that doesn't happen here. We can actually change elements. We can start with uranium, we can change it into lead or change it into thorium or something like that. And the really, really cool thing about fission is that really very small changes in mass, like thousandths of a gram, 1 or 2 atoms sort of decaying, actually releases massive amounts of energy. That's why we can use, the actual core of a nuclear reactor isn't very big. It would fit in this room, and that's enough to power houses and cities for years, essentially. This is why nuclear energy is so amazing, and why it's clean in terms of carbon. No carbon's produced. It's kind of a hot button topic. So there was a guy came up with a formula, E equals mc squared. Does anybody actually know what the formula means, or what the letters in the formula means, or who was the guy that came up with the formula? No, Mr. Borden. The most famous formula in physics, nobody knows who came up with it. Costin, I'll have to get back to you. I'll check my schedule, and I'll send you a message after class. Thank you, Josh. Yes, Albert Einstein came up with this formula, E equals mc squared. What does it mean? Well, E is energy, m is mass, and c is the speed of light squared, which when you really think about it, energy and the speed of light and mass should probably have nothing to do with one another, but Einstein was a pretty smart guy, and he figured out that, in fact, if you take the mass of something and you multiply it by the speed of light squared, you can figure out how much energy is stored in that thing. And in kind of practical uses of this, if I took my mass, 60 kilos or 80 kilos, and multiplied it by the speed of light squared, I would get a massive number, like enough energy to power the world for years. When we talk about atoms breaking down and releasing energy, we're talking about such small quantities of mass. If you've ever seen a nuclear explosion or videos of nuclear explosions and things like that, when those explosions happen, That's about, about 1 to 10 grams of actual matter being converted to energy. So the amount of energy that's stored in you and all of the particles in your being is just this massive amount of energy, and that's why this equation was so crazy. So what we can do is we can take the sort of nuclear equations that we were dealing with before with alpha, beta, and gamma, trying to figure out what type of particle was released or what the new product would be. And we can do the exact same thing here. So if I took a nitrogen atom, take some nitrogen, and I wanted to break down, what I can do is I can take a helium nucleus or an alpha particle and I can fire it really fast at the nitrogen. And what happens is when the alpha particle and the nitrogen come together, they all kind of join together and the atom gets really unstable, and then it breaks down into oxygen and hydrogen. And you'll notice when we do all of these equations, the math always works out. So if I think about this as kind of being two lines, so I have the top line is 4 plus 14, and then this is our equal sign, is 17 plus 1. Well, 4 plus 14 gives me 18 equals 17 plus 1 is 18. And on the bottom I have 2 plus 7 is 9, and that equals 8 plus 1, which is 9. So the math always works out from just like when we were balancing, just like when we were doing alpha, beta, gamma decay. Now we're going to do a little bit more complicated formulas in terms of equations, but the math's always going to work out. So if you can add or subtract, you can do these types of questions. One thing I will mention though, something like a hydrogen atom or just one proton, one neutron, on the back of your data booklet on page 12, there are symbols for a neutron and a proton just in the bottom of the chart here. So if you ever forget what those things are, you can have a look there. So these are just the kind of simplified equations. We're not always going to draw these fancy pictures with protons and neutrons. We can use just the symbols. So 4,2 alpha plus nitrogen reacts to produce oxygen and phosphorus, or not oxygen, phosphorus, oxygen and a proton. Or I could write it instead of a proton, which is one neutron, or one proton, which has a mass of 1, I could write it as hydrogen down below here. So basically in these kind of equations where you have 4 things, generally speaking, you'll be given 3 and be asked to find the 4th one, and it's just a little bit of subtraction to sort of figure out what it is. So here are the symbols for things that you'll encounter, and again, these are all on the back page of your data booklet. So you have protons, 1p, that's the same thing as a hydrogen nucleus. Then you have neutrons, which is 10N, and then helium nucleus or an alpha particle is 4,2 alpha or He, and then electrons 0, -1. We've looked at the alpha and beta already. The important idea here is that if we have an arrow, whatever's on one side of the arrow has to equal whatever's on the other side. It'll always work out. So let's look at 2 examples, or I guess there's only one example here, and we'll try to figure out what we're missing. So basically what this is uranium-235. If I take uranium-235, try something here. Oh, that's brilliant. Now my cursor's where it's supposed to be. Uranium-235 is right here. If I take some uranium and I get a neutron going really, really fast, I get a neutron going and I fire the neutron at the uranium is going to go, oh no, I'm too big now, and then it's going to break down. And there's, I think it's like 18 different combinations of things it can break down into. You never really know which one's going to break into. In this particular example, it's breaking down into krypton and barium, giving off 3 additional neutrons and then a whole lot of energy. Down below here, I'm giving up some cesium, Cs, and I'm starting with uranium. I'm bombarding it with neutrons, and it's breaking down into something different. And I'm asking you to help me figure out what this something is. So the first pair was krypton and barium. This one's a little bit different. I have cesium and something else, and we're going to figure out what the something else is. So let's jump into OneNote. There we go. So we need to figure out what it is. Let's go. You want to kind of think of it as sort of two different math equations. On this side, I have 1. I'm just talking about this sort of the top numbers here. So the top portion. I have 1 plus 235. This arrow is equals. I have something plus 141. And then I have 3 of whatever's here, so 3. And then the energy I don't really need to worry about. So remember the coefficient in front means 3 of whatever's there. In this case, it's just 3 neutrons. All right, some basic math. If I have 1 plus 235, I have 236 on this side, is equal to something plus 141, and 3 is going to give us 144. What is the something? What is the blank? What goes here? If I have an equation, 236 equals something plus 144. Eric, you're a step ahead of me. Do you want to help me with the numbers? If I want to think of the left side equaling the right side, 91. All right, so I have to have 236. On this side, I have something plus 141. So if I think about it in terms of an equation, I can think of it like this. 236 is x plus 144. Solve for x. I'm going to subtract 144 from both sides. What do I get? So 236 minus 144. I get 92. Did I do that right? 236 minus 144. It's looking good to me. So I have 92. So whatever here is 92. No worries. And on the bottom, we're going to do the same thing. I have 0 plus 92 is equal to something plus 55 plus 3 times 0 is going to give me 0. What is that something? Well, that's going to look a little bit like 92 is equal to something plus 55. What plus 55 gives us 92? Or 92 minus 55, what does that equal? That's 37. All right, thank you, Leeds. So what element am I talking about here? I need to figure out what symbol to include. Now I have two numbers. I have the 92 and I have the 37. And which one am I looking for in the periodic table? What element is it? Am I looking at the 92 or am I looking at the 37? Which one tells me what element I'm looking for? Top or bottom? The top is the mass, so that's the atomic mass. And the atomic mass can change, right? If I talk about something like carbon, carbon can be carbon-12. Most of the carbon is carbon-12. But I can still have carbon-14. That's the radioactive carbon. So if I have carbon and I have carbon, which number is the same for all carbons? It's the bottom one. So that bottom number is the one that's going to tell me what element this is. So element number 37 on the periodic table is looking like rubidium. So I want to look at the bottom number always, and this is Rb. So the math has to work out on either side of my arrow. Left side's got to equal the right side. Let's continue on, and I believe we have another example. I thought I had another example. I have another example. Oh, this is a fusion example. I have a feeling we'll get to this in a second. All right, let's jump back into the notes and we'll mosey along here. All right, so we did that. So this is fission, and uranium-235 is really good at breaking down radioactively. So most nuclear fission reactors and weapons use this principle. What you do is you take uranium-235. It's big and it's unstable, and you take a neutron and you fire it at the uranium-235. The neutron makes it unsettled, and the uranium will break down into two things, sometimes barium and krypton. It can be a bunch of different combinations of things. It breaks down and you get 3 additional neutrons that come out of the nucleus, like that. So this is a process that's going to happen over and over again really quickly. Remember, we're only talking about one atom, but if we had a sample, there'd be millions of atoms present, billions. And this is the equation for this exact thing that's happening in the little picture. You get a neutron plus uranium-235, gives you krypton, barium, 3 additional neutrons and energy. So really similar to the one we just did, the example we just looked at. The really cool thing about nuclear fission is that once it starts, we can keep it going. When you get that first neutron, comes in, it gets in the nucleus breaks apart into 2 things. You get 3 additional neutrons produced, and those 3 neutrons can go off and hit other uraniums. And if they absorb them, then they break down. They're each going to release 3 additional ones. So think about that. If we take 1 neutron, we throw it in there, it breaks apart the uranium, and 3 additional neutrons are produced. So the first step, you start with 1 neutron, boom, it breaks apart, now you have 3 neutrons. Boom, those hit, and then now you have 9 additional neutrons. Those all hit, and each time you have an increase of a factor of 3. So this is how a chain reaction works. It can get really, really out of control quickly, and that's essentially what a nuclear bomb is. If you have enough uranium, it's called a critical mass. If you have more than a critical mass, you bombard it with a neutron, it breaks apart, breaks apart, breaks apart. Just, happens so quickly. So much energy is released in a very small amount of time. That is a chain reaction. In a nuclear power plant, instead of taking all of the uranium, making it break down in a very short amount of time, like fraction of a second, what we do is we kind of slow down the neutrons, we catch some, and we can slow down the reaction to control the energy that's released. So instead of trying to catch a bomb's worth of energy in a really short amount of time, we slow it down over long periods of time, and we can trap the energy. So there was a guy named Fermi, and he realized that materials could absorb some neutrons, and that would help us control the speed at which the reaction occurred. And again, once we get really quick breakdown of these atoms, you get massive amounts of energy produced in a very short amount of time, which isn't good for us. This woman here, her name is Liz Meitner, and Liz Meitner was a very, very influential figure in the discovery of chain reactions, nuclear decays, things like that. And if I can teach you anything about the history of science in the last 150 years or so, 100 years, is that women in science were often forgotten. And she was really influential. She was ahead of her time. She did stuff that Einstein would later kind of, discover on his own, but separately. She was ahead of Einstein. She was extremely bright. And there was another guy named Otto Hahn, who also was working on the same stuff, and they worked together. He ended up winning a Nobel Prize for his work, and Lise Meitner did not win anything because she was a female, which is kind of repeated again and again and again through the history of science. Anyways, the joke's on Otto Hahn, because Otto Hahn won the Nobel Prize. Nobody remembers Otto Hahn, but I forget what year it was. The international agency who names elements on the periodic table actually named element 109 after Lise Meitner because it's radioactive, and she had such an influence on this stuff, but she never had any recognition during her lifetime. So there you go. Lise Meitner was one of these women in science that science forgot, but now we're remembering her and acknowledging all the work that she did. Unfortunately, she is no longer with us, but there you go. So she was ahead of Einstein in a lot of stuff Einstein did. Einstein just got a little bit more notoriety because he was a little bit more prolific because he did more stuff than she did. Okay, we should look at a CANDU reactor real quick just so we know what's going on inside there, and then we can talk a little bit more about fusion, and then we'll see what time it is. So we've sold our CANDU reactor technology to South Korea, China, India, Argentina, Romania, Pakistan. They're all over the world. They're very safe. That's what the greatest benefit is. And they can use uranium-238, which is non-refined uranium, which not all reactors can use. And we help all these other countries produce electricity for their people. The problem is that when we break down uranium, so we'll look at this example, maybe we'll look at this one, same thing. Uranium's breaking down into krypton and barium. This krypton and barium is radioactive, and we don't know what to do with it. We can't clean it because it's radioactive. You can't get near it. It has lots of ionizing radiation coming off of it, and we have no way of making it safe, so we just don't know what to do with it. So this is kind of the big drawback of nuclear power, is that you have all of this amazing energy produced, but the byproducts we don't really know what to do with. But we might one day know what to do with them, and that's kind of the hope. So what we do now is we just kind of store them in these big vat container things that are earthquake proof and bomb proof and everything proof, and we just hope that one day we'll be able to use the waste to do something with it. But right now we can't, which is sad. So a lot of times we'll go back and re-refine the old stuff and take out the good stuff that's left in there, but kind of recycling. But most of it's buried underground and stored for basically thousands of years because it'll be radioactive for that long. And there's a couple storage facilities in Canada that are temporary, nothing permanent in Canada yet. The United States has 2 storage facilities for nuclear waste, and actually one of them's not far away from us down in Washington State. And just a couple weeks ago, one of the tunnels that this stuff is stored in actually collapsed, and it released a bunch of radiation in these tunnels, and that was just in the news a couple days ago. So this is what the inside of a CANDU reactor looks like, more or less. So you have your reactor core, not very big. What would be maybe the size of a couple cars, maybe a truck. So this is what your reactor core looks like. These red bars here would be uranium. So we'd stick uranium in, and basically what happens is you get some water that goes in this circuit, and it comes up and gets cooled and drops down, makes it back to the core, gets hot again, comes up, and when it makes it into the second container, there's a bunch of water in here. It heats the water up. The water evaporates, creates steam, the steam gets released into another building, which turns this turbine. And then we take water from the outside, like a river or lake. We run it through here. It cools the steam down. The steam turns back into water, and the loop continues. So there's essentially 3 loops. This first loop is going to be highly radioactive. Well, not highly, but fairly radioactive, this water in here. The second loop, again, is a closed loop. It'll be less radioactive, not very radioactive at all. The second kind of purplish loop, and then the blue loop, the water from the outside, is not radioactive. It just goes in, just collects. We just use it to cool down the steam back into a liquid, and away you go. So that is the essential components of a CANDU reactor. You should be able to just kind of recognize what's happening there. The big idea is that you take something like uranium, you heat up some water, the water spins a turbine. Once it turns into steam, you cool the steam back down to water, and you just do it again and again and again. So this is what's actually happening inside the reactor core. And uranium-235 gets bombarded with a neutron, and it breaks apart, and 3 more neutrons are produced, and those will hit another 3, and those will break apart, and those will release more neutrons. And the problem is, if the neutrons go too fast, they'll go right through the middle of this atom, and they won't get absorbed. They'll just go zing right through it, and it won't actually break down again. So what we need to do is we put these reactors in stuff called moderators, and different reactors use different types of moderators. Sometimes we use heavy water, which is just water with a different isotope of hydrogen in it. Control rods are inserted to absorb neutrons, and control rods control the speed of a reaction. So we don't want a reaction to go so quickly that it basically just obliterates all the uranium really quickly, because then we have no uranium left. We created too much energy. We couldn't harvest it all. So the control rods actually absorb neutrons to be able to speed up or slow down a reaction. And control rods are made of usually graphite, which is just kind of the stuff that's in your pencil. Or there's lots of stuff that's made of graphite, carbon fiber these days. And the graphite just absorbs neutrons, and the graphite controls the speed of the reaction. So the moderator's in there to slow the neutrons down. If you don't slow them down, they just go zing right through the middle, and they don't get absorbed. And the control rods basically get dropped in, and they absorb neutrons that are kind of flying around. They're extra, so that slows it down. If you want to speed up the reaction, if you want to increase the amount of energy produced, you just lift the control rods up a little bit. That speeds up the reaction because there's nothing to absorb the extra neutrons. You want to slow it down, you drop them in, and this is what happens. So this is how we create power. So a little history lesson. There'd be 3-ish radioactive meltdowns so far ever-ish. There's one in New York State called 3 Mile Island. There was one in Chernobyl in 1980, I believe, 80-ish. This is actually a picture of Chernobyl here. And there was one in Fukushima not long ago in 2011. This is this is Chernobyl. This is the reactor core right here that melted down. Basically, they were doing some tests, and a bunch of people did a bunch of silly things, and the reactor got so hot that all of that middle part of the reactor where the reactor core was, it got so hot that it melted. And that's why we called it a meltdown, because the temperature of the uranium got so hot that you couldn't control it anymore, and it literally just melted the metal, it melted absolutely everything. And it's extremely radioactive, this Chernobyl area. So what they've done is they're building this big dome right here. And to give you an idea of scale, you can see some of the cars in the picture down at the bottom here. These little dots are cars. Lost my cursor. There it is. So you can see the little red dots and stuff down here. These are cars. So this thing is like several football fields across. What they're doing is they're building it on these big tracks, and then they're going to slowly move this dome, slide it over until it covers this part of the reactor core. So the radiation's no longer escaping into the atmosphere. It'll get trapped by this big dome. It'll keep water out. And because the half-life for all of these things is so long, this Chernobyl area will be radioactive for thousands of years. The other picture here is, this is the Fukushima Daiichi plant in Japan, Fukushima portion of Japan. What happened is on the ocean, you get the big earthquake happens, and the tsunami comes and hits the reactor. So these are the 4 reactor cores, 1, 2, 3, 4. So the wave comes in, knocks out all the power, so basically the plant goes into kind of shutdown mode. The reactor is all shut down, but they're really hot still. And so they need to circulate water, and they were relying on generators to bring in power because the initial earthquake knocked out power. And the generators all got swamped by the tsunami. So now you have these really hot reactor cores and no water circulating through to cool them down. And what happens is a bunch of hydrogen gas was produced, and you can see the reactors, 3 of the 4 reactors are missing roofs because the amount of hydrogen gas built up that the roofs blew off, and the reactors actually exploded, and that was not too long ago. So that was kind of the second big one. The 3 Mile Island meltdown in New York wasn't as bad as these other ones, but the Fukushima and the one in the Ukraine, they both have created kind of dead zones where nobody lives anymore because of the radiation that's released. Let's just go on to fusion. It just takes a second, and then we'll call it a day. So fission was when you take something really big, uranium or plutonium, and you break it down into 2 smaller things. Fusion is the exact opposite, where you take 2 small things, you can combine them together to create something bigger. And nuclear fusion is kind of what it sounds. So if you ever get confused on fission and fusion, when you fuse something, if you have fusion cuisine, that's where you mix 2 different types of cooking together. Fusion is fusing or bringing 2 things together. Fission is breaking something apart. And when we take 2 small things, usually protons and neutrons, we stick them together, they create something bigger, we get a bunch of energy being produced. This is happening in the sun right now. Our sun is a pretty small star in the scale of things, and our small star takes hydrogen, sticks it together to create helium. Sometimes it can take helium and stick it together with hydrogen to create things like beryllium, but our sun is really small, and it can only fuse things up to about beryllium or so. There are bigger stars in the universe that can fuse things much larger than that. And if you think about it, all of the things that make you and me and stars and whatnot were created in a fusion process in a star somewhere. Stars get really big, they get old, they run out of fuel. If they're big enough, they die. Supernova, boom, explodes, and you get even heavier elements. So the largest naturally occurring element is going to be uranium. Anything beyond that is usually created by us. So we're really working hard on creating fusion reactors, because if we take a bunch of protons, stick them together, we get a byproduct of helium, and helium isn't radioactive. There's sort of no radioactive waste when we have a fusion reaction. But we can't get the temperatures and pressures high enough to make it kind of happen and absorb a bunch of energy out of it still. We're working really hard on it, but we're not quite there, unfortunately. So you can see the reaction down here. We have hydrogen plus hydrogen, so 2 different isotopes of hydrogen, react to produce helium, a neutron, and a bunch of energy. So the byproducts of a fusion reaction are helium, which is really good because helium's not bad for the environment. We're not quite there yet, though. So let's do this example, and we'll see that, yeah, there's crickets in this office. Crickets in the office. We have pet crickets, Herman and Sherman. Herman and Sherman the crickets. All right, so let's look at this guy. Second example. Just like fission reactions, fusion reactions happen And the math works out, except the math's a lot easier for fusion because the numbers are a lot smaller. So let's look at the top. On the top, I have 6 plus 1 equals something plus 4. What is that something? 6 plus 1 should give me 7 equals something plus 4. What is my something? What is the number I am missing there? If you said 3, you'd be right. On the bottom, same thing. I have 3 plus 0 is equal to something plus 2. What plus 2 gives me 3? You would be wrong if you said 26. So this is 1. So when I go and try to figure out what element it is, it's element number 1. And if you have to look that up, that's fine. If you know what element 1 is on the periodic table, you could just write it down as hydrogen. So when we undergo fusion, we can take lithium, add a neutron to it, and it produces hydrogen, some helium, and a bunch of energy. This is why fusion is really amazing, because we can take small elements that we have lots of. Hydrogen's the most abundant element in the universe. Water, H2O. The oceans on our planet have basically limitless hydrogen. And if we can take those hydrogens and stick them together to create helium, we could have enough energy to power the world for billions of years. So we could stop relying on oil, which is bad because it produces carbon. Carbon's warming the Earth. As the Earth gets warmer, our weather patterns change. We get 30-degree weather in May, which is terrific, except if you live near a lake or a river, when all that snow melts, and then the river floods, and the lake floods, and the city panics, and it's just the end of the world. It's terrible. If we could produce all of our energy with fusion, we would have hydrogen sticking to hydrogen, so 2 non-radioactive things like hydrogens. They stick together to produce something like helium, and that helium, you could inhale it and talk funny, and that would be the worst byproduct that would come of it. We're not quite there yet. We can't make hydrogen stick together on Earth efficiently yet. Maybe in your lifetime, probably in your lifetime. Or as the sort of shift away from fossil fuels happen, there's a lot more solar that's kind of happening these days. I'm not a huge kind of history guy, but there is some really kind of interesting stuff in here that I want to talk about. So I'll just give you the Coles notes on this. You can just Google it and read it if you like. This is a letter from Albert Einstein to F.D. Roosevelt, who was the President of the United States, in 1939. So this is kind of in the middle of the Second World War. So you guys study the World War. What grade do you study the World Wars in? I don't think you do it in grade 10. I think it's like grade 9 or 8 or something like that. Grade 9. So you guys just talked about, everyone, just talked about the end of the Second World War. Obviously, well, not obviously, hopefully you know that the Second World War ended when Roosevelt and the United States dropped a couple bombs on Hiroshima and Nagasaki. And those nuclear bombs weren't just something that they had sitting in a back room somewhere. During this whole war effort, the United States was working really hard to develop a nuclear bomb. They believed it was possible, and they wanted to build it to kind of show some force, and it ultimately ended the World War, which was probably a good thing, but thousands of people died instantly when they dropped these bombs in Japan. This is a letter that Albert Einstein, who was working with the United States, wrote to the president saying, hey, this nuclear fission stuff's probably possible, but you shouldn't probably do it because it would be really, really bad. Lots of energy would be released. Nobody really knows what's going to happen. The problem was, at the same time, we were really worried that the Germans were very close to developing the bomb, and if the Germans would have developed it first, it probably would have changed the outcome of the war. This I only show because it has a personal connection to me. These were the places in the United States in 1939 to 42-ish that helped develop the nuclear weapons. And there's lots of really, big sort of ones like Oak Ridge. There was a nuclear reactor happening or producing nuclear energy at the time. There was another one in Los Alamos. Alamogordo was where the first nuclear bomb was ever detonated, the Trinity, Project Trinity. And after they detonated the first one in the desert, not too much longer later, I forget the time frame between the first test bomb being detonated, the second nuclear bomb ever detonated was in Hiroshima, and then a few days later in Nagasaki, and then that ended the war. So there was literally, they developed the bomb, they tested one, dropped two in Japan, and that was the end of the war. Does anybody notice a connection that's kind of close to us that nobody really thinks of in terms of developing nuclear bombs? There's two places in Canada. There's one in Trail, which is not too far away from where we are, and there's one in Chalk River, which is, I think it's on the Quebec side of the river between Quebec and Ontario. But basically in Trail, where my family grew up, not my family, my dad and his dad lived, there was a smelter plant. Has anybody been to Trail, BC before? Sometimes there's, one or two people that have been there. Trail, BC is on the Columbia River. So this is the Columbia River, cruising down through Trail. This second picture is a view from the Columbia River looking back, and you can see this big smokestack with the black top is the same one here. And this is the highway that kind of runs into Trail, and if you were to continue on this road right about here, you would cross this bridge over the Columbia River into the actual city of Trail. But anyways, this big plant takes rocks from all over the North America, and then they melt it down and take things like zinc and nickel and precious metals out of the rocks. During the Second World War, in secrecy, they took this big plant, and because there was so much water in the Columbia, they used it to make something called heavy water, which is water with same amount of hydrogen, but it uses a different isotope of hydrogen. And they needed the heavy water to have this nuclear reaction occur so they could purify the uranium. They needed it for a bunch of stuff. And they made most of the heavy water for the nuclear bomb in Trail. And then they shipped it down into Hanford, Washington, which is not too far on the other side of the border in Washington State. The reason I talk about it is because it has a BC connection. And the second reason is my grandfather actually worked in this plant, as did my father for a short amount of time. My grandfather worked in the plant, and he helped in secrecy convert the plant to make heavy water in a portion of the building. So I think it's kind of interesting that there's this local connection that not many people realize to the creation of the first atomic bombs. And I think it's pretty cool that it happened in BC and not too far away from here in our neck of the woods. So there you go. Usually I watch some videos of atomic bombs being detonated, which is kind of fun in a very scary sort of way. Luckily, we kind of live in an age where we have computers that are powerful enough to simulate nuclear blasts and to try to figure out how to make them more efficient and whatnot. But at the same time, it's kind of scary because we live in a nuclear age where countries can just drop bombs and kill thousands and millions of people in mere seconds. Let's watch this, I guess. I just want to show you a couple seconds of it. It's not super important that we just sit here and watch it. So obviously all of the initial footage of nuclear detonations and whatnot happened in the 40s and 50s. So this is a long time ago. And I just want to jump forward to straight about here. All right, so when a nuclear bomb detonates, basically there's a couple things that happen. Right as soon as a nuclear bomb goes off, a bunch of light is created, and light travels really fast. And basically the light is so bright that if you were to stand in front of this building and you were facing the nuclear blast, with your eyes closed, there'd be so much light created from the nuclear blast, you would literally go blind even with your eyes closed. And the way to kind of think about this, if you were lying in your bedroom, your mom or dad or brother and sister comes in, turns on the light, even when your eyes are closed, everything kind of gets bright. You can still see through your eyelids. And when we talk about how much light is created, the initial blast of radiation that comes off of a nuclear bomb, you get really amazing things happening. So if you look at the pictures here, you can see that just before the big blast happens, you get all of the sort of paint and sidings on the buildings vaporizes instantly. So it just turns to dust. And if you were there, you'd turn to dust too, because so much energy is being released. After you get that, then you get the shock wave, and the shock wave is a pressure blast that kind of knocks things over. And that is what happens during these nuclear detonations. So you can go online and watch lots of unclassified footage, but you get the kind of vaporization of everything, and then the shock wave comes through and knocks everything over. So again here, when this loads in a second, this is a power station. You can see the paint and stuff on the power station, especially kind of like in this area here. Everything just kind of vaporizes that's not strong. All the radiation that's kind of released would burn you. And then you have the shock wave comes through and essentially knocks everything over. And this happens again and again and again. And you can see it, vaporization, and then you get your shock wave, which knocks everything down. So kind of scary stuff. If you've never seen any sorts of footage like this before, I recommend you go check it out. The amazing thing to me to think about is when we talk about these bombs being detonated, in the first few bombs, they weren't really efficient. They would take, several kilograms of uranium and they would split it and you get this big detonation that would be enough to level a city. We're talking about a few grams of actual mass converted to energy. So when you see like, a city flattened, that's like 15 grams, a dime's worth of plutonium being converted into energy. A dime can release that much energy. It just kind of is hard to even believe it when somebody tells you it, but that's in the reality what's going on. So this second video is called the SAR bomb, and the video is not great, but it's the biggest bomb ever detonated, 50 megatons, which is 50 million tons of TNT equivalent. It was a big bomb. And next day maybe we'll start class with the nuclear detonation website thing. I think it's pretty interesting stuff. So there you go. We've been going for a while now, so we should probably have a little quick look at the learning guide, and then I'll leave you guys for today. So we talked about alpha, beta, gamma decay. We've talked about half-life. And then we need to talk about these nuclear decay equations. So just like the examples we did in class, on these few questions, you need to make sure to just try to fill in the blanks, and you just need to do the math. The top lines has to add up on either side of the arrow. The bottom lines have to add up on either side of the arrow. And these are just basic sort of math. And we always look to the bottom number to figure out the element. So this is the 39 tells me it's yttrium. The 94 is plutonium. 92 is uranium. So when you want to figure out what the element is, always look to the bottom time. What else is there in here? It's basically had a few questions about decay, and obviously this learning guide's not quite as long as most of the other ones. So what I'll do is I'll leave you guys with those questions. I'd like you to go through them, especially 4 and 5, because you'll have some of those to do. Those will be due next day. I'll spend probably half of next class, wrapping up this radiation stuff, and we won't start physics until next Tuesday. So Unit 7 No, Unit 8, sorry. We'll start Unit 8 next Tuesday. Let's just have a look at the course, and I will leave you. Okie dokie. So last day I said, hey guys, there's a Half-Life activity in here and I'd like you to do it. And some of you guys had Macs, and I sent you a little message saying, hey, Mac users, you can't do the fun activity, so you can do this little worksheet instead. And I'll leave the option open to everyone. So the Half-Life assignment's right here, and in the Half-Life assignment you have the lab to download the little worksheet. Click on the download button, go through the activity, follow the instructions, fill in the blanks. Ask you to draw a couple graphs, just some definitions and stuff that we've looked at before. If you want to do that, you can, or if you are a Mac user or anyone else for that matter, there's this Half-Life Decay extra practice sheet, and this is what I sent to you guys. But if you want to do this instead of the lab activity, there's a little kind of like a practice quiz that has 12 questions and then some decay equations. You can do that instead. So that's your choice. You can do either one you want, and both can be kind of handed into the same spot, the Half-Life assignment. So that's really all there is for this unit. We'll start next day. We'll talk about a little bit more stuff, and I'll make sure everyone's on the right track, and then we'll be finished this. So does anybody have any questions before we go? Costin, I'm going to have a look at my schedule, and I'll send you a message in Moodle and let you know if I'm going to be around this afternoon. Anyone else? No one else? All right, sounds good. I will leave you guys there. We'll start next day with any questions you guys have. I'll talk about a few more things. I'll go through some examples, and then we're done. Unit 7. That's it. That's all. So have yourselves a great afternoon, and we will see you on Thursday morning. Thanks.